Hey everyone, it's Dr. Bianchi here. I hope everyone is doing well. I have put together this somewhat short, brief video overviewing the independent samples or the two-sample t-test, which is the next version of the t-statistic that we are moving into this week. And you also have a problem on the statistical analysis project that involves conducting a t-test using statistical software. So last week we talked about the single sample t-test where we have one sample and we're testing a hypothesis about an unknown population. Specifically, we're using our sample to represent the population. We use the t-test approach when we lack information on the standard deviation or the variability of the population. And if you'll remember, with the one sample t-test, we compute the standard error. We estimate the standard error of the population by using the sample. This week, we're moving into the two sample t-test, or what's called independent samples t-test. Let me just show you a visual of this really quick. Okay, this is basically our situation. Instead of having one sample, we now have two samples. Okay, here you can see sample A and sample B, and we're using them to get a sense of what would happen to these two populations had they all been exposed to the experiment or the study. So here we have a hypothesis that getting taught by one kind of method is going to be more effective than another. Maybe this semester is a great example for testing something like this out. At first, we were doing in-person learning, and now everybody has transitioned to fully online learning. Many might wonder which is more effective. Is showing up in the classroom live with your peers and instructor a more effective way of learning statistics, or is online more effective? Maybe there's no significant difference between either method. Anyway, just kind of a made-up example. We could imagine that sample A is exposed to fully in-person learning, okay, 3 days a week or something like that, and sample B learns online. At the end of the day, we want to see if these groups are statistically different on the final exam. Does one method of learning link up with higher final exam results than the other, or are they not statistically different? Okay, in the two sample t-test, we're using two samples to test a hypothesis about two populations. Okay, let's go ahead and look at some of the math. Let me just stop sharing this. Okay, if you look on my board up here, I have just in text outlined the steps to computing the two sample t-test. The first step is to compute the pooled variance. Because we have two samples, we need to get a combined estimate of their total variability. Okay, and that's what that S2P thing is in the formula sheet. And in the formula, it's the combined variance. Let me just move my screen here a little bit closer. Okay, the pooled variance is the variance pooled, and you'll see the little p as a subscript. Once you have the pooled variance, then you're going to be able to use that to compute the standard error. In this case, it's the standard error of the mean difference between sample 1 and sample 2. How much wiggle room or error is there in the difference between two groups? And then we can go ahead and fill in our t-test. Okay, so those are the three steps. 1 is pooled variance, 2 is compute the standard error, and 3 is go ahead and run the t-test. And then you'll be using the t-table as usual to make a decision about whether to reject the null hypothesis or whether we can't reject the null hypothesis. Okay, so just give me 1 second here. So how do we compute the pooled variance? Okay, you'll find this formula on the formula sheet like all of our formulas. And I will always give you these different pieces of the equation, so it'll just be plug and play. The pooled variance is equal to the sum of squares for sample 1, okay, plus the sum of squares for sample 2. We learned how to compute sum of squares all the way back in January. Okay, everyone knows how to do it by now. I'm just going to be giving you those values. And then we divide by the degrees of freedom for sample 1, okay, plus the degrees of freedom for sample 2. Remember, degrees of freedom is always equal to n minus 1, sample size minus 1. So if we wanted to compute the pooled variance, it's the sum of squares for group 1 plus the sum of squares for group 2 over the degrees of freedom for group 1 plus the degrees of freedom for group 2. Okay, let's go ahead and try out a problem. Okay, let me pull up my screen here quickly. Okay, this is from the slides. Oops. Let me just, 1 second here, a little technological difficulty. Okay, let's go to one of the problems that we had in the lecture video. Okay, here is a perfectly good problem that we can do together. A researcher conducts a between subject study. Okay, that basically means we're comparing two groups, examining the effectiveness of a group exercise program, okay, at an assisted living facility for elderly adults. One group of residents is selected to participate in the program, okay, and the other group is a control group. They don't get the fitness program. After 6 weeks, the researcher reports a combined score measuring balance and strength for each individual, and the data are as follows. Okay, the control group had 10 subjects. The average score on the fitness test was 12, and here's your sum of squares value, 120.5. Now, the exercise group had 15 people. The average score on the fitness test was a 15.5, and the sum of squares is 190. Does the exercise program have a significant effect? Use a two-tailed test with an alpha level of 0.05 and then compute Cohen's d to measure the treatment effect. What I want you to do right now is take a second and just compute the pooled variance here. Okay, this is obviously a two-sample problem. We have two groups and we want to see if they're different from each other in their fitness. We need to use the two-sample t-test. First step, we need the pooled variance. So go ahead and use the formula that we just worked on to get the pooled variance for this group. Go ahead and take a second to do that, pause the video, and then we can resume. Okay, I'm gonna go ahead here and walk through the math. And I highly encourage you pausing this video, stopping and trying the problems yourself, and then tuning back in. It's a more effective way to learn and master this stuff is to take a shot at it yourself. And then if you go wrong, you can see where the mistake fell. Okay, so this is just gonna be plug and play. Okay, the sum of squares for group 1 was 120.5 plus sum of squares for group 2, which is 190. Degrees of freedom for group 1 is equal to n minus 1. 10 minus 1 is 9. And the degrees of freedom for group 2 is going to be 15 minus 1, which is 14. Okay, so there you have it. Okay, pooled variance is going to end up coming out to 13.5 if you just do that math correctly. Okay, 120.5 plus 190 over 23, you end up with 13.5. Okay, so 13.5 is our combined pooled variance. Why do we have the pooled variance and have to compute that? Well, we have two different groups, and you'll see the sample sizes are not equal. One group has 15 people, and the other group has 10. So the group that has 15 people needs to have more of a say in what the true variability is in the difference between groups. Okay, that's why we compute the pooled variance. Now that we have the pooled variance, we can go ahead and calculate the estimated standard error for the mean difference between groups 1 and 2. This is going to simply be our error term that goes in the denominator of our t-statistic. So how do we calculate that? Well, the estimated standard error for the mean difference between group 1 and group 2 is equal to the following. It's the square root of the pooled variance over the sample size for group 1. Note sample size, not degrees of freedom. We're going to plug in the full sample size here, plus the pooled variance over the sample size for group 2. Okay, let's just go ahead and fill it in. We're going to end up with 13.5 up top because we've already computed the pooled variance. Okay, 13.5. And our sample size for group 1 is 10 people. Make sure you're following this formula properly. They're not asking for degrees of freedom here. Okay, with the standard error, they're asking for sample size. And then the sample size for group 2, which was equal to 15. Okay, so if you plug 13.5 over 10, okay, plus 13.5 over 15 into your calculator, and then you take the square root of that result, you're going to end up with the square root of 2.25, or your final result of 1.5. Okay, this ends up being the square root of 2.25, which is then equal to 1.5. Okay, so our estimated standard error here is 1.50. That's going to go in the denominator of our t-statistic. It's basically our error term. Now we're ready to run the t-statistic. What is the formula for our two-sample t-test? Well, t is equal to the average of group 1 minus the average of group 2. How different are they? We expect them to be probably pretty different if our exercise program was effective. And then we divide by the estimated standard error of the mean difference between groups. Okay, so this is pretty straightforward now. The denominator is 1.5. We just calculated that. And what is the difference between the two groups? Okay, well, let's remind ourselves here. Okay, the control group had a 12 on the fitness test, and the exercise group had 15.5. They're 3.5 points different from one another. There's a 3.5 point advantage on average if you're in the exercise group. So up here, we end up with 3.5. Let's go ahead and calculate that value. Okay, 3.5 divided by 1.5 is 2.33. Our t-statistic here is equal to 2.33. Okay, is that statistically significant? Can we be confident that the 3.5 point difference between the groups and their fitness is due to a systematic effect of the treatment, or is it just due to chance factors? Can we be confident that this treatment would really work if we gave it to other groups and other people? Well, this is where the t-table comes in. So go ahead and pull out your t-table, okay, just like we did for the other example. Now, here's an important thing to remember about the two-sample t-test, right? In order to find the critical t-value on the table, you may remember you need to locate the degrees of freedom. Well, with the two-sample t-test, we take one person away from each group. So it's n-1 for both groups. Now in this example, the combined sample for both groups is equal to 25 people, right? We have 10 people in the control group and we have 15 people in the exercise group. We subtract 1 from each group and we get a combined degrees of freedom of 23. Okay, so for the 2-sample t-test, it's the combined sample size minus 2, 1 from each group. Our degrees of freedom here is 23. Okay, so pull out your t-table, scroll over and go down to 23 degrees of freedom, and then scroll over to the critical t-value for a 2-tailed t-test at the 0.05 alpha level. That's our default alpha level, and it assumes a 5% risk of a type 1 error. If you do that, you will see that the critical t-value is equal to positive or negative 2.069. Okay, let me just go ahead and draw that up here. Okay, so if we're looking at the t distribution, we need to, to reject the null, to find a significant result, okay, we need a t statistic that falls in the critical region here in the extreme tails on either end. And those tails are marked by t-values of positive 2.069 and a negative 2.069. If our sample, the sample difference there, if the t statistic falls in either one of these tails, we reject the null. Okay, the treatment was effective. Okay, I'm just gonna put RN here, reject null. However, if we get a t statistic somewhere in the middle, that is a highly likely outcome if the treatment is not effective. Put differently, we wouldn't have enough evidence to say that the treatment worked. We wouldn't have enough evidence to reject the null hypothesis. Okay, here we can't reject the null. Well, what was our t statistic? We had a 2.33, which puts us in the critical tail and in the area where we now have grounds to say the null hypothesis is unlikely to be correct. It looks like this fitness program had a significant impact on the fitness and health of the participants in the group that went through the program, and we have a statistically significant results. We will be rejecting the null hypothesis here. Okay, so let's recap. 2-sample t-test. We have 2 groups. We want to see if they're significantly different. First step is to compute the pooled variance. Use the pooled variance to get the estimated standard error, and then calculate your t statistic. Once you have your t-value, you consult the t-table, line up the degrees of freedom, and find the t-value that you need to outcompete, and then make a statistical decision, okay, just like we did here. Now we want to back this up with a measure of effect size. Cohen's d is by far most popular. Let's go ahead and compute Cohen's d. With a 2-sample t-test, Cohen's d is equal to the mean difference between group 1 and group 2 over the square root of the pooled variance, okay? The square root of the pooled variance. So you need that pooled variance, not just for the t-test, but also to get Cohen's d, our measure of effect size. Well, up top is pretty simple. Our difference between the 2 samples is 3.5 points. Okay, and if we go back to our problem in the beginning, our pooled variance was equal to 13.5. Okay, so Cohen's d is equal to 3.5 over the square root of 13.5. Well, the square root of 13.5 ends up being 3.63. 7. Okay, so you can go ahead and now plug that into the calculator, and you're going to get a really high Cohen's d value of 0.95. Okay, a very, very large effect size when we're using our Cohen's d evaluation criteria. What does that mean? It means that this treatment, this physical fitness program, improved the fitness of these elderly clients by almost 1 full standard deviation bracket. They improved almost an entire bracket above average by going through this program. Okay, pretty awesome results. Okay, how could we write this up in APA style format, just the way you're going to be asked to do in the statistics project? Well, we ran a t-test with 23 degrees of freedom, and it came out to be 2.33. The probability of a type 1 error, by definition, is less than 5% because we rejected the null hypothesis. Okay, we had a significant result, which means we're confident that our chance of a type 1 error is below 5%. That's what we want. And then Cohen's d was equal to 0.95. Okay, large effect size. Now you might want to write a sentence or two just in basic human language. It appears that the exercise program was statistically significant, as evidenced by our t-test. Furthermore, we had a very large effect size, suggesting that this program had a big impact on the fitness of the elderly residents at the facility. Okay, so that is the overview of the 2-sample t-test. You could also calculate R squared here. Okay, R squared is the amount of variance explained. That would be simple enough to do. You would just use the exact same formula, plug in the obtained t-value, include the necessary components and get the number, and then you could interpret that as well. Go ahead right now and try computing R squared for this problem. You should get a large effect size there too. Measures of effect size should be consistent with one another. So that is the 2-sample t-test. You are now totally ready to go ahead and run the stats project, part 2, and also do the mind tap assignments. I am going to post some practice problems on the 2-sample t-test that are going to count for this week's meeting. So they will be posted right below this video. And I'm also going to have a few videos below this. They're really short, just demoing the stats project, showing you what to point and click in StatCrunch in order to get the results. Okay, so any questions, please reach out. I hope this video has helped. And next week, we're going to move into the final variation of the t-test that we'll be looking at, which is called the repeated measures t-test. It's when we have one sample of people, but we measure them twice. Same group, measuring them at 2 points in time, and we want to see if they've improved or if they've gotten worse on some kind of outcome. So if you want to start looking ahead, start looking into chapter 11. Okay, thanks everyone.